All right, let's dive straight into it. Today's explainer is all about cracking the VG diagram. Now, you probably already know V stands for velocity, or your airspeed, and G stands for the G-forces acting on your wings. Understanding these structural limits is absolutely crucial, not just for confidently crushing your private pilot license ground exam, but for actually keeping yourself safe when you're up there in the left seat. So let's hook right into the most critical question you're going to face, both on the FAA test and out there in the real world. Do you know exactly where your airplane's structural limits truly lie? Picture this. You're cruising along on a hot summer afternoon, right? Everything's perfectly smooth, and then bam, you hit a massive unexpected updrafts. The aerodynamic forces slamming into your airframe literally change in a split second. This whole topic, it's not just about passing a multiple choice test. It's about keeping the wings securely attached to the fuselage when Mother Nature decides to throw a tantrum. You need to know precisely how much stress your specific aircraft can handle before it bends and well before it breaks. Okay, first, we've got to understand a really foundational concept, the limit load. Imagine pulling back hard on the yoke in a steep turn, or maybe during a sudden dive recovery. If you hit this specific load factor, your aircraft structure is going to bend permanently. The metal suffers severe fatigue, and it won't ever return to its original shape. You've essentially compromised the airplane. The wings might look a little warped when you finally get back on the tarmac, and trust me, your mechanic is going to have a very bad day inspecting it. But here's the key takeaway. At the limit load, the airframe hasn't completely broken apart yet. It bent, sure, but it brought you home. On the flip side, we have the ultimate load, and this one is exactly what it sounds like. It is the absolute breaking point. It's the extreme load factor applied beyond that limit load we just talked about, where the aircraft material finally experiences complete structural failure. Simply put, this is where the metal snaps and the aircraft breaks apart in midair. Now, aeronautical engineers are pretty smart, and they generally want to keep us alive, so they build in a specific margin of safety. In general aviation aircraft, the ultimate load is typically 1.5 times the limit load. That 50% engineering buffer, that's your critical gray area between permanently bending your airplane and suffering a catastrophic, unsurvivable failure. Now listen up, because the FAA ground exam absolutely loves to trick you on these two definitions. They'll purposely mix up the wording just to see if you really know the difference. So here's a foolproof memory aid to lock this in for test day. Limit means the metal bends and stays bent, limiting the future life of the plane, but it stays in one piece. Ultimate means it catastrophically breaks, the ultimate bad day. Just think limit equals bent wing and ultimate equals no wing. Locking in that clear, distinct contrast, that is guaranteed points on your test. I know, studying structural failures and wing snapping forces can get a little heavy. So before we dive into the aerodynamic charts, let's take a quick breather. Got a dad joke for you? Why was the airplane sent to its room? Because it had a bad altitude and way too much G-force. Okay, I can practically hear the groans from here. But seriously, managing that G-force and keeping your airplane out of trouble when the air gets rough is exactly what we need to tackle next to master this diagram. So let's introduce your absolute best defense mechanism as a pilot, maneuvering speed. You'll see this heavily tested, and it's denoted on your airspeed indicator as VA. This is the precise speed where your plane will safely stall before it can structurally bend. Think of it like a built-in aerodynamic circuit breaker. If you hit a massive gust of wind at or below this speed, the wings will momentarily lose their lift. They'll abruptly stall, which instantly unloads those dangerous G-forces before they can ever reach the limit load and warp the metal. It's a lifesaver. To really visualize how this works, we need to paint a mental picture of the VG diagram itself. Just imagine a graph where your airspeed increases from left to right along the bottom, and your G-force increases from bottom to top. Maneuvering speed exists exactly at what I like to call the magic intersection. It's the exact point where the curved line of your maximum positive lift capability, going up, perfectly meets the horizontal line of your positive limit load factors stretching across. If you're flying at any speed slower than this point, you literally cannot generate enough aerodynamic force to damage the aircraft from flight loads. As we just discussed, the wing will just safely stall first. Now, what's really wild is how drastically the maximum load factor changes as your speed increases. Let's look at the actual physics here. At a slow 62 miles per hour, pulling back fully on the yoke just gives you a standard 1G wing level stall. No big deal, right? But watch what happens as we speed up. Because aerodynamic forces increase exponentially, specifically with the square of your airspeed, by the time you jump to 92 miles per hour, the aircraft can suddenly pull 2 Gs before stalling. At 112 miles per hour, you're hitting 3 Gs. And by the time you reach 137 miles per hour, pulling abruptly into a stall is going to generate a massive 4.4 Gs, hitting our example limit load. It's crazy how fast those destructive forces build up when you just add a little more throttle. But wait, beyond G-loads and lifting forces, you also have a hard, non-negotiable speed limit. Let's say, for our example aircraft, that number is 225 miles per hour. This is your VNE, your never exceed redline limit airspeed. If you try to fly beyond this speed, structural damage or even complete failure can happen, even if you are flying perfectly straight and level in perfectly smooth air. Why? Because of terrifying aerodynamic phenomena like violent control surface flutter. That's where the wind moving over the wings and tail causes them to literally start vibrating uncontrollably until they tear themselves apart. Yeah, no thanks. It is a hard red line for a very good reason. So when you put all of these limits together, they brilliantly illustrate the overall concept of the flight envelope. On your FAA test, they'll often call this the safe operating boundary of the aircraft. Think of it as a box. You're bounded on the right by your redline speed, bounded on the top and bottom by your limit load factors, and bounded on the left by your maximum lift capability, which is your stall boundary. Any maneuver, gust, or combination of the two that pushes you outside the structural envelope is effectively shortening the service life of the aircraft or causing immediate structural damage. Basically, stay inside the box and the airplane stays intact. Let's move to some practical application and see how this actually builds your real-world safety protocol. When you recognize extremely rough air, like you're entering frontal conditions or, heaven forbid, getting anywhere near thunderstorms, you must immediately reduce your speed to the design maneuvering speed. Here's how that ties back to the diagram. In severe turbulence, Mother Nature is suddenly adding massive G-forces to your plane without you even touching the controls. Slowing down moves your plane to the safe side of the diagram. That way, if a violent gust hits you, your plane will harmlessly stall and drop the load rather than flying right through it and snapping a wing. And it goes without saying, never ever practice high-speed dives or acrobatics in these conditions. Those limits, they're calculated for smooth air only. As we wrap up this explainer, I want to leave you with a pretty provocative question. Now that you've mastered the theory of the VG diagram for your exam, and you know exactly where those boundaries are drawn on paper, do you have the discipline to respect these invisible limits when you are actually out there holding the yoke? The math doesn't lie, guys. The structural integrity of your aircraft depends entirely on your judgment as pilot in command. The sky is very, very unforgiving of those who ignore the physics. Well, thank you so much for studying with us today. If this explainer helped clarify the VG diagram, structural boundaries, and maneuvering speed for you, be sure to hit that like button and subscribe to the channel. We've got plenty more incredibly focused explainers coming your way to help you absolutely crush your PPL ground exam. Keep studying hard, trust your training, and fly safe.